Hello everyone. In this video, we will continue studying binomial random variables and we will see some properties of this binomial random variable. Well, recall that B and P is a random variable that counts the number of successes in a Bernoulli trial with n trials and probability of success given by P. So it just counts the number of successes. Well, the first thing that we saw in another video was that, okay, so you have n trials and you are counting the number of successes. This number of success can be 0, 1, up to at most n, yes? So this is the values of B and P, which is a random variable, can be 0 success, 1 success, 2 success, and up to n success. The second thing is that always there's a way to translate number of successes in terms of number of failures. So always K success in n trials with P, well, if you get exactly K of these n trials as success, then this means that we have m minus K failures in n trials. So if you start counting failures as success, this will mean that you're using n trials, binomial random variable with n trials, but the probability of success now becoming the failure, which is 1 minus P. And while this one was B and P, here we were counting the number of successes. Now, 1 is equal to n minus the other one. So if there are this many successes, there will be this many failures. So that's a relation between these two that you can just write in terms of failure and success. But the last thing that we want to learn here as a property is more like the PDF of binomial random variables are given. We already know how to evaluate those ones. So if f is PDF of B and P, then f at K means what? Means that we are looking for probability of B and K being equal to K. B and P being equal to K. Means that we are looking for probability of getting exactly K successes in a Bernoulli trials with n trials. This, we have a formula from last chapter. This is n choose K, P to the power K, 1 minus P to the power the rest, the failure, yes? And well, just by knowing this, all the events that can be defined in terms of B and P, we can evaluate them using this formula. Okay, let's do some examples here. Find following probabilities. Probability of B502 being equal to 2. It means that we are looking for, let me just write it here, probability of exactly 2 success out of 5 trials. And this is what? This is, well, 5, choose 2. What is the rate of success? 0.2 to the power 2. The rest must be failure, which is 5 minus 2 here. Well, this is 5 choose 2 is 5 times 4 divided by 2 is 10 times 0.2 to the power 2 times 0.8 to the power 3. How about probability of B10 0.5 less than 10? It means that we are looking for probability of less than 10 success in 10 trial with P equal to 0.5. 0.5 is like tossing a coin. Here we are looking for probability of less than 10 heads comes up. While less than 10 means that probability of exactly no, let me write it, no head or success, exactly one success, and up to probability of exactly 9 success. Well, you can do one by one and add them. You have formula for all of those ones. But you see, adding 10 numbers like that, it doesn't, well, you can do it, but there's a better way of doing this, and that is using the complement trick here. You see, if we are supposed to have less than 10 success, I can say that, okay, then the complement of that is going to be more than or at least 10 success. So the complement of that is what we are looking for. The probability of complement we know is that 1 minus probability of the event itself. But remember that the number of successes in n trial at most can be 10. So this is the same thing as writing probability of B10 0.5 must be equal to 10. Because, well, if you have 10 trials, the number of success cannot go beyond 10. Now that it's equality, you know what to do. 10 choose 10, P to the power 10, 1 minus P to the power 10 minus 10. This is 1 minus 10 choose 10 is 1. This guy, this is 0, so that number to the power 0 is 1. The remaining will be 0.5 to the power 10. How about this one? Probability of, so probability of having more than 1 success. So that's exactly what it says. So probability of more than 1 success in 8 trials and P equal to 0.1. Well, you can say that, okay, then it means that we have 2 success or 3 success up to, at most we can have 8 successes if we have 8 trials, yes? But again, there are 7 numbers there that you have to add. The trick again here is that you see this as complement of probability of at most most one success. So the complement of at most one is at least or more than one. Well, that means that I can write 1 minus probability of having at most one success. At most one success means that either we have no success or we have exactly one success. So here 1 minus a choose 0, 0.1 to the power 0, 1 minus 0.1 is 0.9 to the power 8. Do you see this minus sign? This is going to be multiplied inside. So that's why I'm putting that there. So a choose 1, 0.1 to the power 1, and then 0.9 to the power 7. And if you do these ones, you see there are nice numbers here you can calculate. So this is 1 minus 8 choose 0 is 1. So we have this is 1, this is 1. That means that the first term is 0.9 to the power 8 minus 8 choose 1 is 8, 0.1 times 0.9 to the power 7. And that's the number that we were looking for. How about this one? Okay, so probability of getting successes between more than one success and less than or at most 4 success. Well, this is the same thing as saying we are looking for 2 success or we are looking for 3 success or probability of looking for 4 successes. Well, for the first one we have 9 choose 2, 0.3 to the power 2, 0.7 to the power 7 plus 9 choose 3, 0.3 to the power 3, 0.7 to the power 6. 9 choose 4, 0.3 to the power 4, 0.7 to the power 5. And that way we find the numbers. Okay, so you can simplify, but basically you can write that formula for this probability. So you not only need to know the notations for the binomial random variable, you can also evaluate the probabilities and know some properties of this random variable.